Hi everyone, thank you for coming to my talk. I'm Ryuji, and I am going to talk about our recent work on the one-shot manipulation of dynamical quantum resources. So this is a joint work with Bartosz Regula, who is also at NTU Singapore, and also shares the first authorship with me for this work. So let me first give you the brief summary of these contributions in this work. So we introduced a general framework of dynamical resource theories that is described by the quantum channels. And that also encompass the situations with some structures, such as non-local boxes, measurement incompatibility, and quantum contextualities. And we characterize these single-shot resource transformations in this general framework with respect to the resource measures based on the entropic divergences. So what is a resource theory? This is a framework to deal with the quantification and manipulation of physical quantities that are considered precious under some given setting. So the next example is always entanglement theory, where you consider a set of separable states as a free states and a set of local operation as a classical communications, LOCC can be a free operations, and you're trying to manipulate your entanglement only using LOCC. And you're also motivated to quantify the amount of entanglement using the entanglement measures. But you can generalize this idea to other quantum resources as well, such as quantum superpositions or quantum thermodynamics. And this is a nice thing about resource theory. And the natural question here is now, what can we say even while keeping this general picture? So this is interesting because it gives us, it allows us to extract the universal features that are shared by a wide class of quantum resources, and it also gives you a further insight and a good understanding of the peculiarity of the resource too, by comparing that to the properties that should be shared by the other broad class of resources. But it's usually hard to get anything meaningful without assuming anything. So usually we put the assumption that we consider convex resource theories, which is a theory that has the convex and closed set of free objects. But this is a quite mild assumptions, and which is satisfied usually in the many interesting theories. So what is the good question that we should ask in this general framework? So one example is the one-shot resource transformations. So this is a quite general problem, and that is involved in pretty much any quantum information processing, and potentially quite relevant for the physics problems too. So this is asking whether you can transform some given state rho into another state sigma only using the allowed free operations. So an interesting subclass of this question is the distillation and dilution problems. This is widely studied in the entanglement theories as an entanglement distillation and dilutions. So in this situation, you're given some noisy state rho, and using the free operations, you try to distill out some pure reference state, such as Bell state. And this is distillation. In the dilution is the opposite direction, where you start from some reference state and try to realize some desired state rho using the free operations. So recently, it turns out that this can be characterized by the fundamental resource measures at the level of general resource theories. But this is about the quantum states, but quantum states are actually just a special cases of the more general class of quantum resources known as quantum channels. As pointed out by Mark Wood's tweet recently, and I thank him for allowing me to use his tweet in this presentation. So he pointed out that state is a quantum channel, which is true because the quantum state preparation, which is a quantum channel, is considered as a state. And the quantum measurement is also a quantum channel, as you know. And unitary evolution is again quantum channel. And discarding system is a partial trace, a special case of quantum channel. And of course, quantum channel is quantum channel. So, and in practice too, it is quite essential and important for us to deal with these quantum channels as a direct resources if you are particularly interested in the dynamic part of the quantum systems, such as quantum communication, quantum computations, or quantum optics settings. But more than that, what's hidden in this statement is that the quantum channels can also include more interesting situations. Not only the quantum channels that transform the quantum states to quantum states, which has been main focus of the studies of the quantum resource theories of channels, but also such as Nonlocality, which has some specific structures. So Nonlocality is about something called boxes, which is the classical transformation. You take in the classical input and you output the classical variable, but this can be recognized as the bipartite quantum channel. So this is some quantum channel with a structure. And this was extensively discussed in the recent paper by Schmidt et al. And Rosette et al. But we can also generalize this, ideas to the different quantum dynamics too, such as quantum contextuality, which is again about the box transformations. You take a classical variable specifying the context of measurement and output some measurement outcomes. Or you can consider the measurement incompatibilities, which is defined for the set of measurement, the ensemble of measurements. But this ensemble part can be realized by adding another classical variables as an additional input to the quantum channels. So this can be accommodated in the unified picture. And if you carefully deal with it, and this is one of the contributions of this work. So how do we transform the quantum channels? So it's widely known that the channel transformations can be done by quantum superchannels, which can be also composed by the quantum channels. So with this, we can now set up our corresponding resource theories, which encompasses many general situations where we have now free channels instead of free states. Then as a free operations, we can consider the free superchannels, where we define the free superchannels as the one that does not create a resource for channel out of free channels. And we can also consider the functions from quantum channels to real numbers as resource measures. And so then now we can ask what is the formal way of treating these channel transformations, which could also have some structures. So suppose that this is a set of all channels, then you can consider some subset of the channels, and this can be the channels of interest. For instance, if you're talking about the nonlocality theory, then the non-signaling boxes, which has a classical input and a classical output, can be the channels of interest. And you can also consider the subset of the channels inside of this. And this is a free, you consider this as a free channels. For example, local hidden variable boxes can correspond to this. And now consider the super channels that transform this structure to another structure, which can be different from the initial ones, but still can have some specific structure again. So we consider a subset of super channel SO as the interested super channels, and we can now define this free super channels that map the set of free channels into another set of free channels. So now we can, in this framework, we can now connect, we can discuss the one-shot resource transformations and trying to connect this to a resource quantifier. And we can set up the analogous question analogously to the state transformation case, where we consider the transformation between the E and N within this channels of the set of channels of interest, then consider the transformation using the free super channels here. And we can also consider the distillation and dilution problem by introducing the family of the pure reference channels, which corresponds to the Bell states in the entanglement distillation and dilution case. And then now we try to characterize these transformation rules with respect to the resource measure that can be defined for the general dynamical resource theories, which we will do next. So for the first measure, which is quite relevant in this work, is a robustness type measure. So robustness measure is, intuitively speaking, how robust your channel is against the mixture with another channel. Then depending on the channel that you can mix with, there are two types of robustness measures. The first one we call the standard robustness measure. So this is the given channel E, and you try to mix some channel M so that the mixture of them becomes free. Then you take the minimum mixture level and define it as a standard robustness measure. But this M should be inside a set of free channels, whereas this generalized robustness measure, this M can be any channel of interest. So this can be outside of the free channel. So that is why, by definition, this generalized robustness is smaller than or equal to the standard robustness measure, and sometimes they are equal to each other. And for later use, we also define the smooth version of these measures so that we can take into account the finite error that comes with the one-shot resource transformations. And to give you a little bit more familiarity for the generalized robustness for some of the audience here, this can be recognized as, so like if you take a log of generalized robustness, this is exactly the same as max relative entropy measure. So this is a quite familiar measure for the quantum communication, and this is in the family of Renyi divergences. If you take a sandwich-Renyi generalization, then if you take alpha infinity, then you reconstruct a Dmax. Then, as we saw, even though the standard robustness is not in this family, but we have a relation between the standard robustness, the generalized robustness like this, and the generalized robustness is the max relative entropy. So we can now establish an interesting relation between the standard robustness and these Renyi family measures. And you can also look at another quantum generalization of the Renyi divergence, and you can find this mean relative entropy measure at the other side of the spectrum. Then this is related to the operational task known as hypothesis testing, and this is precisely the second measure we are going to look at. So this is the hypothesis testing relative entropy measure if you take a log of it, and you can convert this to the channel measure by taking the optimization over the input state. So this is related to the operational task where you are trying to distinguish between these two channels E and M, okay, and by using some input channel input say psi. Then you also make a measurement at the end. So you can also convert this hypothesis testing measure into the resource measure by taking the minimization over the free channel M here. And so we call it the hypothesis testing resource measure, but we can also define the variant of such a measure. We call it a affine measure because we are taking the minimization over affine Hall of the free channels. So this affine O is the affine Hall of the free channels, where this Ri is a real number and sums to 1. So this is a affine combination of them. So by definition, the affine one is smaller than or equal to the usual ones. So then we can also introduce a variant of a special case of that, where this is a mean relative entropy measure. So this corresponds to the error 0 case. And you can also, again, convert to the channel one and convert it to the resource measure by taking the minimization over the free channels and affine Hall of channels. So one of the reasons why we need to introduce these several types of measure is that we find that, interestingly, depending on the classification of the resource theories, the characterization of the transformation can be different. Then this classification is carried out, these are classified by the geometry of the set of free objects. So we first introduced the four-dimensional theories whose free sets free sets are finite measure. So meaning that we have a finite volume. So if you take a span of these elements, and then you can cover the channels of interest. So this includes entanglement theory. This is related to the fact that any entangled state can be represented as a linear combination of the separable states. And this also includes the nonlocality theory and also magic theory. By the way, this picture is precisely for the theory of magic, which has the tetrahedron stabilizer Hall. And we also introduce the we also call the other theories reduced dimensional theories, which has the zero measure free sets like this. So if you have, so for instance, this resource outside of this plane cannot be represented as a linear combination of the free objects, and this includes the theory of coherence or asymmetry. And when it comes to dynamical resource theories, this includes the non-signaling assisted communication, as we will mention later. Or quantum thermodynamics is another example of the reduced dimensional theories. So with this, we are in a position to state the relation between the resource measures and the one-shot resource transformations. So we heavily use this notation where if there exists a free superchannel that transforms this channel E to N within the error E measured by the fidelity, then we write like this. Then we can state some necessary and sufficient conditions for such transformations. So if there exists such a transformations, then for any arbitrary resource monotone, and so we also take the smooth version of the resource measure like this, and this should always satisfy for any resource measure for any delta satisfying these inequalities. And this is, roughly speaking, just the monotonicity properties, but this also integrates the non-trivial, the error trade-off. So if you are allowed to have the finite error, still like this inequality should hold. And also, we can get a sufficient condition for transformations. If this satisfies, then there exists such transformations. So this sufficient condition can be described by now the hypothesis type resource measure and the robustness type measure here, depending on the full dimensional theory or reduced dimensional theories of interest. Then this is the standard robustness measure. Then this is the generalized robustness measure. So depending on which theory you are thinking about. Okay. And so this is the general characterization of the resource transformations. But if we look at the more specific case of distillation, and we can say a bit more than that. So we consider specifically the target channel, pure target channel, in the sense that if we input some pure state and we always get the output, pure out state out. Okay. Then as an example, this includes the pure state preparation, and that reduces to the state transformation problem, or unitary gate, which is another standard way of choosing the target dynamical resource. Then for these situations, we can get the necessary and sufficient condition in this way, where now we use the hypothesis testing resource measure. And so so necessary condition tells that hypothesis testing measure should decrease, and like this is greater than the mean version of the resource measure for the full dimensional theories, and correspondingly for the reduced dimensional theories. And for the sufficient condition, we have now the hypothesis testing resource measure and the standard robustness and a generalized robustness measure like this. So note that so these measures had initially the totally different operational perspectives. Like this is the hypothesis testing problems, and this is the mixture of the two resource, two channels like this. But now we put some operational applications to these measures in terms of the one-shot resource transformations. So using these results, we can exactly characterize the one-shot dilution cost and one-shot distributable resource. So this is considered for some set of the family of reference channels as works as a currency. Then the one-shot dilution cost is the smallest resource content in the family of the reference channels that you need to have to realize this given channel E by free super channel. And the one-shot distributable resource is the maximum resource content you can get from the given channel E by using the free super channel. So this is analogously, again, defined for the entanglement, distillation, dilution, but this is for the channel transformations. Then now we can state the exact characterizations of the one-shot dilution cost and the one-shot distributable resource in terms of the standard robustness measure, hypothesis testing resource measures, and also for the reduced dimensional theories, the generalized robustness measure, and a fine version of the hypothesis testing measure for distillation and dilution cost. And so these conditions can be quite interesting, but this is satisfied for many interesting situations like entanglement theory for the Bell state, or coherent theory with the maximally coherent state. And for some of the situations of the quantum communication, we will see that these conditions are actually satisfied too. So the significance of these results is twofold. The one is that we now gain the general characterization of resource exchange in the sense that if you're given some noisy channel, you can trade it with the reference channel as a current which is a currency, or you can pay that currency to realize some desired channel. And this transformation condition can be now characterized by this fundamental resource measures. And also from the resource theoretic perspective, we can also provide these resource measures with the operational interpretations, which is quite nice because once you get some resource monotone, you need to have some, you want to have some meaning to it. So this gives you the universal way of seeing this operational significance for such a resource measures. And on the and by the way, there's another slightly different way of looking at this distillation process. So instead of looking at the conditions, we can also see the performance of such a distillation process by looking at this maximum distillation fidelities. And in these recent works figured out that we can nicely bound this maximum distillation fidelity using the generalized robustness as well as the weight measure. So weight resource measure is defined in this way, which is quite similar to the robustness measure, but it's quite different actually. Then these bounds also behave quite differently to each other. And also, like, these results can be applied to the transformation that involves the multiple channels. So this can also include the parallel manipulation, adaptive cone, and also even the channel transformation, which involves the infinite causal orders. So please take a look at these papers if you're interested in details. But the point for this current work is that we can now extend these results to the more general settings, which can have some structures like non-locality, incompatibilities, and contextualities. Then especially these weight measures were introduced under the different names for these settings like this, and non-locality contents, incompatibility weight, and contextual fractions. So like these or weight measures, and we can now get the operational applications of these weight measures in terms of these resource transformations. So let me talk about some applications of the general results. So that these general results can be applied to many settings, but I will just mention a small number of examples in which the dynamical resource can play active roles. The first one is the quantum communication, where these capacity and simulation cost play a major roles. So the capacity is the maximum size of the identity channel that you can realize by this noisy channel by using the allowed encoding and decoding. Our simulation cost is another one. The minimum size of the identity channel you need to realize this noisy channel by allowed encoding and decoding. But you can see this allowed encoding and decoding as allowed free super channels. Then you can recast this problem into the one-shot distillation and dilution problems in this result theoretical framework. So this gives the fresh perspective of these quantum channel theories. And specifically for the separability preserving codes, for instance, this is an example of the full dimensional theory. And one can check that this inequality holds. So we can apply our result and state that this quantum capacity and channel simulation cost is characterized by the hypothesis testing resource measure and a standard robustness measure recovering a previous results. And also for the non-signaling assisted codes, which is related to these constant channels being the free channels, this is an example of the reduced dimensional theories, and one can check that this equality holds. So this gives you the exact characterization of quantum capacity, quantum capacity, and simulation cost. And the quantum capacity was phrased as a solution of the SDP problem before, but now we explicitly stated as the fine resource measure, and also this simulation cost was obtained for this specific setting, but we reconstruct this from this universal unified techniques. And we can also talk about Bell non-localities by setting these channels of interest as a non-signaling boxes, which is the classical channels, and local hidden variable boxes can be the set of free channels, and we can consider the free super channels being the local hidden variable preserving super channels. Then there have been several measures of non-locality proposed before under these names: the robustness of non-localities, a generalized robustness of non-localities, non-local content. This is the weight measure of the non-localities, or mean resource measure, which I think introduced here. So this work provides the operational applications to these measures in terms of these resource transformations. And we can also calculate these measures for the isotropic boxes like this. And more generally, we can actually get that if you consider this class of the boxes for the P strictly greater than 0, then we can find that this mean measure is always 1, which is the smallest value for any n. Whereas this PL box has a discontinuous value, which is strictly greater than 1. So this implies that if you don't allow any error, then no matter how many boxes you have, you cannot realize the perfectly pure box. So this was observed before by using the totally different techniques. So we recovered this fact using this resource theoretical argument, and also this is true for the extended class of free super channels that can be much strictly greater than the one discussed usually. And also, we can talk about the measurement incompatibility that is defined for the set of measurements. So the set of measurement is called compatible if there exists a parent P of VM, so that we can realize these measurements by post-processing the results of these parent measurements. So to gauge the incompatibility of robustness, this incompatibility robustness, the quantification of incompatibility was proposed like this, and this is defined at the level of the measurement ensemble. So they mix up this the set of measurements so that the resulting set of measurement is compatible. But we can also integrate this measure into our setting, unified setting as well, by considering this kind of bipartite quantum channels with some classical variables here, and using the TQC channel, using the compatible set of measurements. And we can find that we carry over our definition of the generalized robustness and find that this generalized robustness is exactly the same as this incompatible robustness. And we can also employ the similar arguments to different resource measures as well. So we can now provide the operational applications to these measures of incompatibilities. So in conclusion, we introduced a general framework of one-shot resource manipulation applicable to a broad class of dynamical resource theories involving some specific structures, and we characterized one-shot resource transformations, in particular one-shot resource dilution cost and distributable resource in terms of resource quantifiers based on some entropic divergences, such as the robustness measure or hypothesis testing resource measures. And we apply those general techniques to the concrete examples in which the dynamical resources play active roles. And we found the operational applications and interpretations to these resource measures in terms of the resource transformations. So these resource measures were separately introduced for a specific setting. So we integrated them in the unified framework. So as a future work, it will be interesting to take in-depth study on the resource transformation for nonlocality or measurement incompatibility or quantum contextuality and so forth. So we slightly did that for the isotropic boxes, but it will be interesting to extend these ideas to the more specific, situations using these resource theoretic perspectives. And it is also interesting to have a general characterization for the relation between the different resource measures. So to state the results, we use like this condition, like a mean measure and a robustness measure. Then we have many examples satisfying this relation, but we don't have general characterizations of it. So it'll be interesting to investigate when does this happen. And finally, it'll be interesting to connect our one-shot results to the asymptotic transformations. So this might involve the evaluation of the resource measures to the asymptotic level, which might involve the highly complicated mathematics, but also it'll be interesting to employ some techniques introduced here in which we were able to get some insights into the asymptotic channel transformations as well as the transformations that involve the multiple number, like n number of channels to the reference channel, like in terms of the distillation. So then please take a look at these papers if you're interested, and also there's a talk for the second work as well. So with this, I thank you for your attention, and please feel free to let me know or send me an email if you have any questions or interest. Thank you very much.